Model of Machine Replacement and Maintenance by Thompson. And I think last time we derived the bank control. We also got a term here saying that if this quantity is less than zero, then we use zero control. And if it is bigger than zero, then you use the maximum control U. And if it is equal to zero, then of course it's a singular control. This one can be interpreted, and I think we did it last time, but let's just continue with one more time. It is actually the present value of the marginal return from increasing the preventive by $1 at a time. So if I increase the preventive, so this is about preventive maintenance, and as opposed to necessary maintenance, which you have to do anyway, so there's no control there. But here it says that if I increase the preventive maintenance by $1, what shall I gain? And if that gain is positive, then I increase, right? As much as possible in this case. So the last term, which is e to the minus rho t, right here, in the argument of bank function is the present value of that $1 spent preventive maintenance at time t. So if I spend $1 at time t, and remember we are doing this finite horizon model, and so we are actually using the standard maximum principle. And the standard maximum principle, the value function and everything is computed at time 0. So if I spend $1 at time small t, then the present value of that $1 is e to the minus rho t. That's the money going out. Okay. Once again, remember when you do marginal analysis, we say it's $1, but usually it's per dollar. So usually it's epsilon dollar, epsilon going to 0. Is that how you do marginal analysis? But the language is such that we say, let's increase it by $1 at a time. Okay. So that is the outgoing cost of maintenance. So what happens if the marginal return of $1 of additional revenue is more than $1, then perform the maximum maintenance, otherwise do not perform at all. And we already interpreted that when we did the interpretation of lambda. We already interpreted that value as the value of the additional sales. The state variable here is the sales value of the machine. And so if you increase by preventive maintenance a little bit of extra sales value, then that is the value of an extra sale value. So that's sort of how you get the interpretation of the policy as well as lambda 2. So the next thing we have to do is find out what the control is, characterize the control. And we know that this is the switching function, and we want to analyze the switching function. To analyze the switching function, there is a one term missing here. Rewriting this, and we take the derivative of that with respect to t, and we take the derivative of that with respect to t. That is that then is even an exercise 9.1. And if once you take the derivative and you recognize the fact that pi divided by rho is bigger than 1, otherwise we don't want to be in the business of producing with this machine anyway. And so given that and the GT is decreasing, once again, I tell you that every time you write a paper, you may write non-decreasing, but every time you want to talk about it, it's better to talk about saying it's decreasing. You will see somewhere that if you have lots of non-decreasing, non-increasing, your brain doesn't function. Maybe yours does, but mine doesn't. So it follows that there will not be a singular control because it's monotonically decreasing. So we get two things out of it. If it's monotonically decreasing, strictly monotonically decreasing, then we're not going to have any place where the switching function will stay at 0. And if it doesn't stay at 0, then it is only at one point, and we don't care about it. The second factor is that if it's monotonically decreasing, then the control can only go from U to 0. So we maintain maybe more in the beginning, and then we don't maintain towards the end. Now, that means that there are 3 possible control scenarios. You can have a 0 all the way. That means you don't maintain the machine all the way to T. Or you can have a U all the way, which means we maintain the machine fully all the way to T. Or we can have a U for a while and then 0. And if that's the case, then there's a switching point. At switching point, this will become 0. So if we set that equal to 0, we'll find the switching point. So there is a switching point T sub S, and we can characterize the solution of the problem in this way, that the optimal control will be U for T less than Ts, and it'll be 0 for T bigger than Ts. Now, if you set that to 0 and solve for small t, it's possible that the solution is negative. If it's negative, then we set Ts equal to 0. Okay, so when Ts equal to 0, it means the solution is Ts is 0, so solution is 0 for all the way. Other way is the solution is greater than big T. If it's greater than big T, the machine only goes up to T, so we'll set Ts equal to T. And if you set Ts equal to T, then by this formula, it means the machine is going to be maintained at large value of U for entire time interval. And if it's in between 0 and T, then we have this formula. So this formula is good for every solution of this, provided we decide what we interpret by solution in terms of Ts. So so this is the Thompson's big contribution here was that he also not only he wanted to maintain the machine properly, and there are a lot of models in the literature that maintain investment and machines or by using control theory or otherwise. And there are a lot of models that replace the machine without doing the maintenance. And I have a number of papers on that as well, called machine replacement problem. So there are machine maintenance problems in the literature, there are machine replacement problems in the literature, but this is the first time that Thompson integrated the replacement problem with maintenance problem. And this was a paper that was in Management Science. This was part of the course he was teaching, and everybody was writing the paper. So this is his contribution to that class. And we can use the terminal time condition on T star. We have that formula. And so we can simply use that. And this is the condition satisfied by T star as a decision variable. Then the problem is we have this solution that depends on T. And T is decision variable. So we have to somehow put this guy and this guy together. And that is an important aspect of this problem. And we will see how Thompson does it. So what he does is the following. Suppose that so we're now looking at these two equations, that one, and trying to figure out how to manage this business of free terminal time. So it means that if U star T star equal to 0, that means if the control at the end is 0, which can happen either if the control is 0 all the way, or control is U and then 0. There are two ways that can happen. But if it is 0, then we can substitute 0 here. If you substitute 0 here, this also means that if U star T star equal to 0, then Ts is less than T star. If you look at this thing, it means Ts is less than T star. This means this condition, Ts is less than T star. And that means that either Ts is 0 or Ts is somewhere below T star, so that control will either always be 0 or control will be U and then 0. But in either case, when U star T star equal to 0, we must have this equation. That means whenever U T star equal to 0, our salvage value should have this formula. Now let's say if U star T star is capital U, then it's clear that Ts equal to T star. Because if the end solution is U, then it is going to be U all the way. So now we can substitute U in there for U star T star, and we get this formula. So you can see that by doing this condition, by using this condition, we have got a condition on X star T star. What should be the value of the state variable, which is the sales value of the machine at time T star? Now try to read this sentence and try to immediately figure out what it means. Since dt is non-decreasing, gt is non-increasing, and xt is non-increasing, equation 9.13 or equation 9.14, whichever the case, has a solution for T star. Right? So it's difficult to parse this. But if you say dt is decreasing, non-decreasing is increasing, dt is increasing. If dt is increasing, and let's look at this, if dt is decreasing, and if dt is increasing and xt is increasing, then this would have a solution. That's easier to follow. So say increasing, decreasing, and decreasing, the sentence will be easier to understand. But when you write the paper, you still have to change it back to non-decreasing. So that's just the way. So the first thing we do is we can find that there will be a solution. Now, in order to illustrate all this, Thompson begins with an example. And I think that is reasonable to do because all the work is done, and it is better to illustrate that with an example to see how we can put all these things together. So equal to 1, x0 is 100, dt is 2, pi is 0.1, rho is 0.5, the discount rate, gt is given by this formula. Then the state equation 9.3 will become this. And condition on Ts by equating 9.10 to 0, 9.10 is given by this formula. This is our switching function. And when we set equal to 0, you get Ts. So we're going to put set equal to 0. The condition we set equal to 0. This is the condition for Ts. So we know that switching function would satisfy this condition. Now, this is the situation here. In doing so, we have assumed that the solution of 9.16 lies in the open interval 0 to t. That means it's an interior solution. So what Thompson is doing now is to first take the interior solution and try to see how far he can go. And then he will also say that, as we'll indicate later, the special care needs to be exercised if this is not the case. The problem has to be solved in whichever way, and it has to cover all the cases that one can encounter. So we substitute the data in these equations, pi and rho and all that, and we find that the Ts satisfies this equation, which can simplify to this 9.17. Once I know Ts, I can integrate x dot equation, which is the 9.15 here. I can integrate that. But now in integrating this equation, I have to first integrate up to Ts. And up to Ts, my control is U, capital U. So I have to integrate that equation with the capital U here, and then get all the way to Ts. And after Ts, I would switch the control to 0 and integrate again, given the initial condition at Ts. So if you do that, you get xt equal to this. It's just integrating. This is the equation equal to that, and if equal to this if t is bigger than ts. So this is before ts. I think one should say before ts and then after ts. I don't know why I didn't put it there, but it should be there. Since we assume this, we substitute. So we assume this, we substitute xt into 9.13, which is the equation that we obtained by this guy when ts is less than t star. I'm now using this condition. This is our transversality condition for t star to be optimal. You cannot not use it. We can use it. So we have, so we obtain this, we substitute xt, and we obtain this from that equation, which can simplify to t equal to this. So now we have an equation t and ts, 9.18, and we have another equation in t and ts. And we know if we have two equations in t and ts, we should be able to solve, in most cases, for both variable capital T and ts. This is how you get simultaneously. You see what I'm saying? You can't solve ts without t and t without ts. So we have to get all of those equations put together to get the two equations, and the two equations can be solved simultaneously. And so we solve 9 simultaneously, substituting 9.18. I can substitute, because this is solved for t, I can substitute that equation in the 9.17, which is that one. And I can find out that for 9.17, we have a solution. We can only have equation just in ts, because t has been, capital T has been eliminated by 9.18. So we have only one variable equation, but that's a transcendental equation. There is usually no closed form solution for most transcendental equations. And so what we do then is we're going to do a numerical solution, which is very easy to do for any one-dimensional equation. So we can write a program. This was done long time ago, in the late 60s. So they probably didn't use Mathematica or anything. Anyway, Thompson used a search program and find the TS to be 10.66. So that equation gets solved for 10.6. Then you put 10.6 here and you find T to be 30.4. So TS is 10.6 and T is 35.8. So we have no anomaly here. We actually have that, and that was our assumption to begin with. If we begin with that assumption and we solve the solution, solve the problem, and we get that, then we are done. And so we can basically see what the solution is. The solution is capital 1, because capital U is 1. So maintain at rate 1 up to 10.6 and then go to 0. And then you can substitute these guys in the x equation. TS can be put into this x equation, and you will see that the way the salvage value goes down, it starts with 100 and then goes down slowly because you are maintaining at 1. So the salvage value will be retained to some extent, and you will slow down. And with that happens, then at 10.6 we switch to no maintenance. We cease maintenance, and then it goes a little bit faster because there's no maintenance. The salvage value goes faster to a lower value, and at around 34.8, this machine will be sold at $40. So the optimal solution now consists of maintenance expense here, and you get some money when you sell it at the sale date, and we had all of that into the problem formulation of this. If the solution did not satisfy this condition, suppose I had TS and T became bigger than that, then this would result in either TS equal to 0 or T is equal to T. So what happens is when this is not satisfied, we go to the other case. When you go to the other case, there are only two cases left. Either TS has to be 0 or TS has to be T. So if TS equal to 0, we would obtain T from 9.18, which is that one. because Ts equal to 0 is still condition that would be more like this. And so what we do, we don't need this guy anymore. No, we don't need this where is, yeah, we don't need that one of the Ts equation anymore because Ts is set at 0. And then you put this 0 here and you find T. So that's one way to do it, or the only way to do it. On the other hand, Ts equal to T, Ts equal to T, then we are completely in a different this situation, because then we are not going to be able to use this condition, we are going to be able to use this condition. And Ts equal to T, 9.13, wherever we use 9.13 is no good. So we have to replace 9.13 by 9.14 and redo the calculations of whatever. And then we will find out that we already have Ts equal to T. We already have Ts equal to T. Sorry. And so all we need to find out is what capital T is. So one variable is already decided, the other variable, we have an equation for that, and we can do that. Neither the paper nor Thompson find another example. So one day I should do it. If I give you a different data for which one of these two solutions will be optimal, then that would be a good exercise. But this requires some work to get different data, to keep trying to figure out which one will give you that other case, and then make that as an exercise. So there can be two nice exercises. If somebody is willing to do it, let me know. And then you will have these two exercises, and that could be that could use the other part of the model. So any question, because we just finished the Thompson model. We have four model in this chapter. It's a rather large chapter, and I think a very nice chapter, a very, very, very wonderful use of optimal control theory, because what we're doing now is not so easy to be done in many other ways. And so it is, and it is also not, it's not what I'm saying is, it is not something that you can quickly find out and do an intuition. Of course, you need intuition in some, but you cannot simply explicitly obtain the solution and verify the maximum principle. So this is the step of which a published paper, publishable papers are made. The rest is the second model is very simple, in the sense that people don't want to have bang control, because this is not really very practical. Most of the real life models may not go this way. That's because the problem is linear, and maybe world is not linear. And in that case, G function is a function of U, T, and T, and it's a nonlinear function. And one can do a reasonable assumptions on those functions. For example, G is increasing and concave, which means that G sub U is bigger than or equal to 0, which means as I increase maintenance, G will increase, but it will increase at a decreasing rate. So the maintenance is going to be less and less effective as time goes by. Or no, as more and more U is put, then the marginal diminishing value of the maintenance would be. For example, if you have a car and you spend maybe, let's say, $100 every 6 months for maintenance, or every 2 months for maintenance, then there is some value of that. But if you spend $1 million for maintenance every 2 months, it's not going to give you much of the increase in salvage value. Remember, we are not allowed to increase the salvage value of the car. We are not allowed to change the car to something that is not a car. You cannot, add wings to the car and make it fly, which can be possibly done if you spend $1 million or more. But that's not what we want to do. So we have an assumption here that maintenance can only slow down the degradation of the salvage value, but it cannot increase the salvage value. And so this kind of assumption is reasonable. But anyway, all I'm trying to say is that when you do something like this, you can use the maximum principle. You're going to get a SAT function where the solution of this equation is given by some function over time, u0t. And in this paper that I wrote in 1973, you can do this analysis and do a little bit more. So what I've done there um, is with those assumptions, I just tell you what one can do. You can show whether u is decreasing, and then you can show whether depending on the assumptions. So what I've done so when SAT function, you will have a control. You have a maximum maintenance up to a certain time, and then you move to this singular control, uh, which gives you an interior control between u and 0, and you maintain the singular control by maintaining that quantity to be 0. That means you select the u, that's u, in order to keep this 0. Okay, that's what you do. And so you can keep that as 0 for a while, and then you can sort of see that this is the solution. If u0t is above capital U, then you set u. If u0 is below 0, then you set 0. But if u0 is in between, then you set u0 equal to u0t, ut equal to u0t. So in my 1973 paper, by taking these are simple things, you should be able to do this. No point doing this calculus here. But I just want to mention here that in that paper, I went as far as showing that the control is decreasing and then 0. Notice that this is more saleable in practice than this control. That and that, right? What I did is, by doing the DT, you might sort of go like this. Okay, that's sort of what is going on. So that looks a little bit more realistic. But I did not go as far as showing whether this is this way, or this is going this way, or this is going this way. That can be done, but it would require a little bit more specification on G, because right now I was able to go 2 derivatives of G. But if you want to do further to see what is the characteristic of this curve, I drew it as a concave function, not because but well, not because, oh no, here, since G trivial is therefore obvious that u0 dot is less than 0. So that's all we can do. Beyond that, you need a little bit more analysis, maybe some specification of G, and also that's not going to give you much of a publication potential, because I think most people are going to be satisfied with this control, and then you can just say that this is one way, and there may be other ways, but we did not go that far to investigate. Now, the second model in this chapter, or the third now, is a phenomenal departure from the Thompson model. And this was also done in that same class, but this was done by two professors at Carnegie Mellon who were also students in that class at that time. Everybody was taking the course, including the professors, and they wrote a paper. And this paper is done by Mort Kamien and Nancy Schwartz, and Kamien died a few years ago. He was a professor at Northwestern after he moved from Carnegie Mellon to Northwestern, and he wrote lots of papers with Nancy. And he also have a control book which competes with my book, but I think they are more successful than I am because they wrote a book for economics audience, and they keep revising the book as time went by, and my book revised. My book got the second edition. First edition was 1983. The second edition was 2000. So it took 17 years for me to revise the book to the second edition. And so I wasn't keeping up with the Joneses in this case. But now I think their revision is done, and I am now go to 4th edition, and I think, in my opinion, my book is definitely better than theirs. That's what I think. Okay, so let's. But this model is very good model, and I'm going to spend some time describing this model. And this model has been used by many people afterwards, and including me and Alain Ben-Susan wrote recently a paper in Management Science that actually redid this model in a more rigorous way, because I think the Kamien Schwartz model is little less rigorous than what some people would like. But the results are correct. That means non-regress but correct results. When I send my paper with Ben Susan to Kamien, he was still alive at that time. He said, "Well, I'm so glad to know that my results are correct." And so we're going to now discuss this model as in Kamien Schwartz, because the one with Ben Susan and Seth is somewhat more complicated mathematically, and it is not finding any room in this book other than a reference. So T is the sale date of the machine to be determined. So Thompson's T continues to be determined. UT is the preventive maintenance, and it's between 0 and 1. Now, what Kamien Schwartz is doing is allowing the machine to fail, break down. And if the machine, so suppose you decided to keep the machine for 5 years, and then the machine failed after 2 years, then the machine has to be junked. That possibility has to be taken into account. Even though you decided to keep the machine for 5 years, machine is decided not to stay with you for 5 years. Okay? So, I mean, that's life, right? I mean, everywhere you plan something, but the plan doesn't pan out, and then you have to do whatever you have to do. R is the constant positive rate of revenue produced by the functioning machine independent of its age. That is not exactly a very realistic assumption, because machine may decline over time before it fails. But in order to make the problem manageable, and this was, after all, the first such model in the literature, I think that assumption is justified, and of course this paper was also published in Management Science, and so we're going to say that, okay, this is our assumption. If you want to do more, then there are other papers that can extend this, but this is what it is right now. Rho is the constant discount rate, and L is the value of the machine when it fails. Whenever it fails, you junk the machine, you get this value. This value could be negative, because you have to get rid of the machine. Let's say if it's a car, you have to get rid of the car. Sometimes you have to pay for it. Or it could be positive, because the junkyard will salvage the tires and things and whatever that is salvageable, and they will pay you maybe $100 or so to say, okay, I'll take the car and I will salvage it and sell parts to people. So whatever it is, Kamien Schwartz decided that L is the positive junk value of the machine. Please ask questions anytime. I'm assuming that you're reading this material, so you're understanding it as I go along, and as you can see, at the speed where we describe these things, you need to have some understanding of the problem before you come to this class. BT is the resale value at machine at time if it is still functioning, and B dot T is less than 0. So what Kamien Schwartz is saying, that as long as the machine is functioning, its rate of production is not going to decline. However, you think about the car can still drive 70 miles on a highway even if it's 5-year old. So it's producing more or less at the same rate. But if you sell the car after 2 years versus after 5 years, you're going to get different value of that car if you sell it. So the sale value of the machine is declining, and is declining, as you can see, B dot T is less than 0. What is the difference between this model and Thompson's model? Well, Thompson's model, the sale value was controlled by maintenance. Here, Kamien Schwartz is saying city sale value is simply a function of time. Maintenance has nothing to do with it. But what they did is that the maintenance changes the probability by which the machine will fail. So their maintenance is speaking to the breakdown rather than speaking to the salvage value. Okay, so that's a difference. And that difference is significant and gives you a different model. Now, how they work in the dynamics with which the maintenance affects the breakdown probability is rather interesting. And it is interesting in 2 ways. One is rather innovative in terms of control theory problem. But the other way is that even though it is a stochastic problem, Kamien and Schwartz were able to solve that as a deterministic control problem. And when Ben Susan and I worked on it, we actually solved that as a stochastic control problem, which is a, I don't want to say anything more than that, but that's way more rigorous. I will mention one remark where the rigor might not be here, but the intuition is correct, and the solution is correct. So that's how it is. So HT is the natural failure rate. It's also called hazard rate in reliability theory. You will see this term in statistics. You will certainly reliability theory if you ever took a course. Most of the time, this course is taught in IE departments, not in business schools. And you will also see that in marketing if you're doing Bass model. Frank Bass was a professor at UTD, and he had a famous advertising model called the Bass model. And the Bass model is based on hazard rate. And in fact, when I wrote a paper with Frank Bass, I did not call it a Bass model. I call it a hazard rate model because I ended doing something more than I ended something more in this connection than Bass was going to do. So hazard rate is positive and is increasing. That means machine's natural failure rate, as it gets older, it's increasing. It's more likely to fail when it's older than when it is not. Okay. Cost of function depending on the preventive maintenance and the natural failure rate. So if I were to use U as my maintenance, my cost will depend on U, but it also depends on H at that time, whatever that is. And remember, we are controlling this, so we will see what's going on. So that's the cost. Assumptions are very sensible in economic sense. Clearly, we are assuming L to be bigger than or equal to 0, but certainly L cannot be bigger than BT, because BT is the value of a functioning machine at any time T, and L is the value of a failed machine. So no matter how far you go, how low this can go, we still want L to be lower than that. Okay, so that's what Kamien Schwartz is assuming. And sort of similar to Thompson in some way, the functioning machine has a salvage value, and that salvage value cannot be bigger than what is its economic value when it comes to production. So because the functioning machine is producing at rate R, and suppose it never breaks down, then it produces the rate R at all the way from 0 to infinity, and its capitalized value is R divided by rho. So the R divided by rho is absolutely the most you can get out of this machine in terms of present value, even if the machine did not fail all the way to infinity. So BT must be less than equal to RT by rho. Remember, all of these assumptions are needed when we try to see whether the function, whether the expression is positive or negative or increasing or decreasing. All of these assumptions are needed in some way or another. So we can just make those now. But they are sensible. The cost of reducing the failure rate, we're going to assume this is nonlinear in U and H, but we're going to assume that it is nonlinear in U, but is linear in H. Simplicity. That means that if I were to maintain preventively at U, when the natural rate is H, this is my cost. In other words, when the natural failure rate is H and a controlled failure rate H1 minus U is sought. So what I think we are a little bit ahead of what is going on. Let me what Kamien Schwartz is doing is the following. He said the natural rate is H times 1, which is H. But if I put maintenance, which is between 0 and 1, then I can reduce the failure rate by this formula. So suppose I use the control maintenance half, then the natural control failure rate is H divided by 2. So I half the natural failure rate. So that means I've in expected value, I've increased the life of the machine. Okay. So the control failure rate, so if natural failure rate is H and I want to seek that control failure rate, then cost of that action is this, CU times H dollars. So that's why it depends. It can depend on H. Okay. It is natural to assume that C0 is 0. If I don't put any maintenance, cost is 0. If I put in more maintenance, then its cost is positive. And too much maintenance is not going to do a good job for us. So CUU, the cost of that would be high, very high. So you will never, that will automatically tell you don't maintain at too high a value because it's not going to help you too much, because it costs you too much. It's one way to say it's not going to help you much. The other way is to say it costs too much. If it doesn't help you too much, you have to do it here. So that will become nonlinear. But if you want to keep this linear and get almost the same result by increasing the cost, you can do it here. So that's what Kamien and Schwartz are doing. You notice when this control book is written for management schools and economics people, and it is not electrical engineering. Electrical engineering will not make all these remarks. They will basically say this and get done with it. I'm now saying, what this does here versus here. We make this linear. We keep the cost increasing at a convex rate. That means that higher the cost, higher the maintenance, way higher the cost, and so no higher maintenance will not be used. And within the region of low maintenance, linearity can be still assumed. So that's sort of what is going on here. Here comes the seminal contribution of Kamien and Schwartz. The reliability theory, the hazard rate is given by this formula. So H, which is the hazard rate, is equal to this formula. That is the definition. So denote the conditional probability density. This is the density. This is the cumulative distribution. So you take the derivative of the cumulative distribution, you get a density. So, but you divide by 1 minus f, so you get a conditional density. So what are we doing here now? Denotes the conditional probability density for the failure of the machine at time t, because the t is always there, right? We don't write t all the time, but it's always there. Given that it has survived up to time t. That means 1 minus f is the probability it did not fail by time t. Ft is the probability, go back to Ft. Ft is the cumulative probability that the machine has failed by time t. So 1 minus Ft is the probability that machine has not failed by time t. And F dot is the density of the rate at which the machine is failing at time t. So those are the things that you need to know. And then Kamien and Schwartz said that hazard rate can be controlled as follows. If I don't put any control, then this is the hazard rate, which is the reliability theory hazard rate. But if I control it, then I can define the control hazard rate this way. That means it's less. More you put, less is the hazard rate, and so you got this. Now notice, I can put 1 minus f on this side and call this as a state variable. F dot, this is a state variable. It's like x dot, and this is control u. This is again x. So it is a state equation. If it's a state equation, then as far as control theory is concerned, it doesn't care whether whatever it is, it is just a state equation, it's a differential equation. Now, the interesting or not interesting, the aspect that Kamien and Schwartz may not have appreciated all that much is that this is not observable. X, I observe. If it's an inventory, I observe. If it's a goodwill, I observe. But this I don't observe. How do you observe the probability of a machine? There's no way to observe it. All you can do is calculate it mathematically and say what it is. Because if I give you a control u, you can integrate this equation, begin with 0, and you can find an ft at time t. So mathematically, I can compute it, but I certainly cannot observe it. And that's where the difference between my model with Ben Susan, that was also published in the same journal, and Kamien Schwartz model. So what Kamien Schwartz do is objective function has to be an expected value because machine is failing at some probability, and so we have to take the expected value. And this is where they were lucky. They found an expected value that works. It's intuitively correct, but mathematically we cannot say that by doing so the solution will be obtained, will be optimal. I'll tell you why I'm saying that in a bit. The reason is that when I solve this problem, okay, let's get to this first. The expected present value of the machine in some of the expected present value has two terms. One is the total revenue it produces less the total cost of maintenance. Well, this is the total revenue it produces at any time t, that's the rate, and that's the cost of maintenance. And this is incurred as long as the machine is functioning. So I multiply by 1 minus f, and that gives me the expected value of this term. The second expected value is the junk value. Well, the junk value is L, and is failing at the rate f dot, which is the probability density. So I can put LF dot and I integrate it. So that, and then there's e to the minus rho t, so that's discounting everything, present value. So I can get the expected value of the value that we obtain when machine fails. And it may fail at t and another t or another t, we don't know when. There's a potential that it can fail anywhere from 0 to capital T. And that potential has to be integrated because machine can only fail at one time, but its rate of fail is a different time, and I can integrate that. And finally, I sell the machine at value bt, and I multiply that by my 1 minus ft because I can only get bt if the machine is still working at t. Right? Now, you may ask why I don't put L times f of t. Because if the machine failed exactly at t, then I would get, because if it failed before t, then there is no t. The business is finished. There's no capital T anymore. Even though t star was 5 years, machine failed 2 years, the problem finishes at 2. But if the machine failed exactly at t, then you can put bt times L, but bt times L times 0 because it's only at one point. It's already there. That the rate of which a machine is failing at t is contributed by taking the integral from 0 to t. So all I need to do is salvage value provided the machine has not failed. This is intuitively very correct, and that's what Kamien and Schwartz do. And notice f dot dt, you can change that to df dt, and df dt you can substitute from here, or you can substitute f dot from here. So you can go there, f dot. Then I have this formula, and this formula is a Meyer form. No, the Bolza form, because it has an integrand which has a u and a f, and it has a salvage value which has a capital T and f of t. So I can use the Bolza form of control theory given this state equation, and I can solve the problem. But what I'm trying to say, that when we solve the problem, we will find a control u star of t all the way from 0 to t. Because remember, no probability is left. For control theory work, it is a deterministic control problem. The probability lives in our head because we know what f is. But control theory only knows f as a state variable, and it has a differential equation, and it has an objective function, and expected value has been obtained by us using the formula of probability. So all of that is good, but notice I find the control all the way from 0 to t, but I only exercise that control only up to the time when it fails. After it fails, the maintenance that I plan to do is not going to be done. And it is not being, it's not going to be done, but and we are not taking that value of u, even though it tells you what u star t is after it breaks down, we're not integrating that here. So we're integrating that by this probability. So that will automatically take care of the rate only up to the time when this, but there is the formulas allow us to compute everything all the way to capital T, just in case machine did not fail before T, capital T. So there is a lot of things going on which are all in our head and not on the piece of paper where it's written. So one could argue that the problem has to be formulated as a stochastic control problem, which is not which is different than the stochastic control that we will cover in at the end of the book. This stochastic control problem is more complicated than what we were going to cover, and that's why I don't cover this in the book at all. So now the standard part comes in. So Kamien Schwartz, more or less, their main contribution is done. The second contribution is just solving the problem, which is really not a huge contribution because given the control problem of this kind, more or less anybody can solve it, and so we're going to solve it. What I've done more than what Kamien Schwartz did is something you will see soon. So Hamiltonian is straightforward. Lambda dot is straightforward. Lambda t comes from the derivative of this guy is straightforward. All of this is good. And then one more condition, which is if the t has to be determined, I use 3.77, which is the terminal condition for t star to be optimal. By the way, this is exercise 9.8. So this is derived in 9.8. I do it here, for example. So this condition is rather complicated. Kamien Schwartz doesn't really give you a good explanation of what it means, because if I give you this condition for optimality of T star and ask you to write an explanation of that in words, it is not that easy. So this is where um, sometimes this is where our publications, our referees would like you to do when you write a paper and submit it. The referees will say, okay, I got this complicated equation, but what is this meaning? Can you explain this? Can you do an interpretation of it? And sometimes the difference between a published paper and a rejected paper is that you were not able to do it because it's complicated. Sometimes it's rather complicated. But okay, that paper survives because the contribution is sufficient up to here. And if you don't make a contribution here, well, okay. But I am doing it. But it has taken me, no, I mean, I've done this right from the first edition, but in each edition, I have improved this to a point that I have now come to the conclusion that my interpretation of this formula now is now, there's no way I can improve it any further. It is so clearly laid out that you will see how many steps it took for me. Every time I rewrite this book, I improve it. So this is fourth improvement of this interpretation. And Kamien Schwartz has one interpretation. So this is the fifth. If you think about it, it's the fifth improvement of this interpretation. So let's now give this interpretation very, very, let me see how we are doing in terms of time. We're still okay. So let's see, let's assume now that this T star satisfies this. So the T star is our optimal solution. How do we want to interpret this condition? Well, try to figure out what happens if I keep the machine for a little bit longer. So let's say I will keep the machine up to T star plus delta. And I have to show you that if I keep the machine T star plus delta, then my value will decrease. So I cannot keep the machine longer than T star. Otherwise, what if I sell the machine before T star, which means delta is less than 0? Well, you can do the same analysis for delta less than 0, and I'm asking you to do that in exercise 9.9. Okay, I don't want to do two analyses in the book, so I do just one. So let's begin. When you do exercise 9.8, this is easy to do. You can take derivatives and stuff. You just substitute things. But then what happens is all of that is multiplied by this factor. It's a common factor in all of this. So what you see 9.34, the 3.77 is this times that. But since this is equal to 0, I can kill it. I can remove it. But if I remove it, the interpretation has to be recognizing the fact that it was there to begin with. So when I remove this, mathematically, no problem. If I don't want to interpret, then I'm done. I don't have to do anything. But if I want to make interpretation of this, then interpretation of R and interpretation of this times R are two different things. And so we need to recognize that. So I'm going to now tell you what I mean by this. Because I remove this, remember this Kamien Schwartz is also done in the standard maximum principle. And so it's not current value maximum principle. So the objective value function is at time 0. Everything is at time 0, present value at time 0. But if I remove e to the minus rho t star, then that value is not at time 0, but is at time t star. So what I'm trying to say is that when I interpret this condition, I'm really at t star, not at 0. And I'm increasing the, so I am at t star, and I'm saying, should I sell the machine now, as the control theory people tell me, or should I wait another delta period of time? So I can do all the calculation at t star. to make that decision. I don't have to bring all of those back to 0 to make that decision, because it's going to be the same decision. After all, e to the minus rho t star is positive. So it's going to be the same decision no matter what. Let's look at what happens when I kill this one. Well, if I remove that, it means that we are at t star and we find the machine to be working. Because if I remove that, I'm also saying f star t star equal to 0. Because that makes it 1, right? And so if I remove the whole thing, it is same as f star t star equal to 0. F star t star to 0 means machine hasn't failed. So what I'm trying to say is that it is okay for me to be at t star and assume that machine is still working. See, that formula is what it is. And what I am now trying, and it's not 0, because if you compute this, solve this f dot, and with the control u star, it may not be 0. Because if it's 0, we will not put ft here, right? It will be just bt. But it's not 0. But notice what is going on. If I am at t star and deciding whether to sell the machine or not sell the machine has to be working. So if it's not working, I have no control over it. It goes for value L. Only time I can say whether I should keep the machine one more delta more time is only if the machine is working. So let's assume the machine is working when I have t star, and that's tantamount to saying f star t star equal to 0, and so I can really remove all of this. So that's the first part of interpretation. If I do that, I don't have to keep this thing all the time with every term, because these terms are already big. So it's better for me to don't have this burden all the time when I speak English. So now we are here. Now the next slide. So if you keep the machine to t star plus delta, then we certainly lose the selling price bt star, because I'm not selling it at t star, so I'm not getting it. I may get it at t star plus delta, but that's what I'm going to find out. What happens? Each thing that is going to happen, I have to do a bookkeeping of it. So I know that I'm not going to get that, but I will gain. I lose this, but I also gain. What do I gain? Well, first thing I gain is that I get a little bit of a more production from the machine in the next delta time. So this is my revenue at that time. If you look at the formula, this is what is going on here, R minus CU, right? This is what's going on. So I'll recover that, but I'm integrating. So when I integrate from T star to T star plus delta, which is delta is very small. Remember, delta is very small, so I can just simply multiply it. Don't have to integrate from T star to T star plus delta, because delta is going to go to 0 eventually. I have to take limit delta go to 0 to find this, so I might as well just multiply by delta. And because I'm getting this production, I need to also bring everything to T star, so I put the discount rate. And I want to equate that to this, because I'm going to open it up with Taylor series, with the delta being small. So e to the minus rho delta is going to open up like this. E to the minus rho delta is 1 minus rho delta plus O delta. So when delta goes to 0, that one is higher order term. So by doing this formula here, I put it here, I get this. So that's one part. Same thing, I do the same thing here. I'm saying that there is a possibility that machine fails because I took the risk of keeping it delta, and I'm unlucky. And because I'm unlucky, the machine failed. And so the machine failure is right there. Again, we use this formula, so get that. The third thing is, if the machine is still working, then I will get the value of the working machine. The value is now not BT star, but it's BT star plus delta. And the fact that it will survive the delta period of time is this probability. And then I discount again. So if I do this, I have to do Taylor series on this one, which is this one. BT star delta is BT star plus derivative of B plus T or delta. So that's something I'm going to put here. And I also have to open this one. So f of t star delta is f star t star plus f dot t star delta. Then I can substitute the value of f dot. I go all the way, and I get this. But since we said f star t star equal to 0 here, I will do that. And when I do all of this, I can take this formula and I derive this side. These are all Taylor series, and I gave you how you do that. So now we are left hand side is all the gain that we make, and the right hand side is all the values that we get, because we open up. So they're the same, left and right the same, but they are simplified expression that I need to do. So now the net gain is the sum of 9.35, 9.36, 9.37 minus BT star, which I lost. So net gain is sum of these guys minus that guy. So that has to be calculated. So 9.35 gives the net cash flow from T star to T star delta. 9.36 represents the junk value, L multiplied by the probability that the machine fails during the short time delta when the machine is found to be working at T star. See, all the languages, everything has to be there. And 9.37 less BT star. So this is the 9.37 minus BT star. It has three terms. That term, that term, that term. And I need to interpret all of that term else as well, because those are interpreted easily, but that is more difficult. Now, what are the terms in there? Well, the first term is very easy. Because I did not sell the machine at BT star, so I don't have that money in the bank. And so I don't earn interest on that money up to from T star to T star plus delta. So that interest is right this one. BT star, if you were in a bank for delta period of time, I will, an interest rate rho, then I would gain that much, but since I don't have a BT star, I will lose that. So I lost the interest. What is the second term? The second term says that the value of the machine decreased from T star to T star plus delta. And the decrease is exactly B sub T T star times delta, because the B sub T is the rate at which the machine is declining at T equal to T star. And I multiply by delta. So that is the decrease in the resale value. So that is the decrease in resale value. And it's negative. So I'm losing this. Okay, so I lost this one, I lost this one. This is negative. You see, it's less than 0 because B sub T is less than 0. And what's the third term? But the third term is I lose the entire resale value if the machine broke down. I don't get anything. I don't get anything with this probability. So the third term, the loss of the entire resale value if the machine fails with the probability this, given that the machine was found to be working at time T star. If you do all this together, 9.36, 9.37, 9.37 minus BT star, you put it all together, you get exactly 9.34. No, well, the delta has to go to 0. So I'm sorry, I missed one term. So if you put all of this together, that's the net gain. If you keep the machine delta and then let delta go to 0, you get the marginal profit of keeping the machine from T star to T star delta, and that has to be equal to 0. So what we're now saying is if we separate the revenue term on one side and the cost term on the other side, we can actually say that this equation is marginal revenue equal to marginal cost. or the marginal revenue minus marginal cost equal to 0, or marginal profit equal to 0. Whichever way you want to call it, you can call it. But we have now provided an economic interpretation of this highly obtuse looking condition, which by looking at it right away, you have no idea what it is. But if you parse it slowly and meticulously, one by one, and peel it like an onion, you will eventually find that the core is exactly this equation. So that's a lot of effort, and it is not in management science. If they were to allow a technical note, maybe I will write a technical note, but management science doesn't allow technical notes anymore. But it is quite a bit of in my opinion, it's quite a bit of a contribution, but it's in the book, so it's okay. It's already published. Any question? So we're gonna finish this model because the rest of it is rather pedestrian. I mean, it's just a little bit of math here and there, and we can just do that. So the optimal maintenance policy for fixed T, first I do for fixed T, just like Thompson did. And so fixed T, and you set H u sub equal to 0. And if you set A equal to 0, there are trivial cases that we have to avoid, because there are two trivial cases. One trivial case is HT is 0. That means machine is not going to fail. Deterministic problem. The other one is Ft equal to 1. That means I know exactly a time at which machine will fail. There is no control. Control doesn't do anything. So those two problems, there is no optimal control problem because there is no control doesn't do anything. So we can remove those conditions. And once you remove those conditions, so this H goes away. So we can remove the H. E to my rho T is positive, so we can remove that. And Ft distance, so we can also remove this guy, and we get this. So when I do that, it means I have to assume H bigger than 0, F strictly less than 1. When I assume H bigger than 0, F less than 1, I can remove these terms. I'm left with this part. This part says same thing, like we did in Thompson models, not the Thompson, but the nonlinear version of Thompson model that I did. Okay, so it means that if this is the condition, then u start equal to 0. If at 1, if it is less than 0, then u start equal to 1. And if it is in between, then you find a control which is between 0 and 1. So this is just maximum principle there. And if you can do the same thing at capital T, because at capital T I know lambda. And lambda T is this guy. So I can substitute E minus rho T here. And then that will cancel with E to the rho T plus. So what's left is just BT. So if I do it for capital T, I get this. At capital T, if this is true, then that. So I know what is happening during the interval from 0 to T, and I know what happens at T. And the Kamien Schwartz goes basically characterize the problem by calculus, and to show that there are these two time intervals. They could be 0. T1 could be 0 in particular. T2 could be T in particular. But if this in the first interval the control is 1, then second interval is a singular. The third one is 0. So control it almost looks like the control that I obtained in 1973 for a deterministic problem. It sort of looks like this: T1, T2, T. And they also don't figure out what is going on here. So they stop this problem by saying that this is the form of the control and that U0 dot itself is decreasing. All of that can be done by Kamien formulas, Kamien Schwartz model, and in doing, you will need these conditions. You will need these conditions and these conditions to figure those out. So that is exercise 9.7 for you. Kamien Schwartz has most of it anyway, but it's still an exercise, and it's a 9.10 exercise also there. So these two exercises gives you or there's even one more. Or sufficiency follows from theorem 2.1. So this also. So that's done. So before we go to the next model, I want to set some scene here, and then we will break. The next model is a model by me and Morton. Tom Morton was a professor at Carnegie Mellon, and I was a student at the time, and I was looking at these problems, and I was saying that machine replacement problem without maintenance is a long literature. There's even a treatise by Machine and Applied some institute, MAPI is called. Machine is not a single machine. After you replace the machine, you need to buy another machine. Then you replace the machine, you need to buy another machine. So there are two possible scenarios. One is that you have an infinite horizon problem and you have to buy the machine one after the other because company is not, it needs a machine. You can't just sell the machine. If you do that, it's a different problem. Because in order to find the first replacement, you need to also, the second replacement will affect the first replacement. After all, it's a simultaneous one global problem. So the problem is different. But it's complicated. Without maintenance, people have solved it to some extent. But with maintenance, it is even more complicated. So let me tell you that there are two possible approaches. One is that I will assume the horizon is infinite and each machine has to be kept the same amount. So if I decide to keep the machine for a year, then every machine has to be kept for 1 year. And our job is to find out whether that optimal time is 1 year or 2 years or 1 year, 3 months or whatever. That is our optimal decision and maintenance for that. So that's called a chain of replacement problem or chain of machine problem. And I wrote this paper. I think there's a reference. If there's an exercise where you're asked to do that, and there is a reference that I published paper in IEEE Transactions somewhere. But the problem that I always had there is that this assumption, which is made in the literature, is not really a very good assumption. Because machines technology is changing. And if it's changing, how can you say every machine has to be kept the same amount of time? Look at the computers. We were keeping the computers. I have bought the first IBM PC in 1970s. I still have that sitting under my desk. If you ever come to my office, you will see there's a computer sitting under my desk, which is the first IBM PC that came out. I still keep it. I think it still works if you keep putting wires and stuff. And I just keep a couple of pair of shoes on it. But anyway, that is my keeping that for whatever. So that, but now you don't keep the computer for so long because new computers come out with much more functionality. Same thing with the cell phone. You don't, unless you were me, who keeps the cell phone for a long time. But most people, when they have a new thing, they either sell their old one and buy a new one. And so there's a replacement problem. And it is not possible to assume this in real life. And it was bothering me for a long time. And so I finally worked out the problem. And I solved that problem. Part of the solution I will mention to you later, and why Morton came into this picture, is the one that I'm going to do later. So I'm going to sort of say I have, so this is the setup I'm going to do, and I'll give you a little story about it, and then we break. So I have a T period problem. I'm going to do discrete time. So that is now, this chapter is really after 8, because I'm actually going to use a discrete maximum principle. Okay. So there are times T1, T2, TL minus TL at which the machine has to be replaced. So what is the optimization program? The optimization program is to find the number of machines that will be needed between 0 and T. I don't know that. That has to be optimized. And once you find the number of machines L, you have to find out where of each machine will be bought and replaced. So we need to find these times. This is simultaneous. You don't find these time and L separately. It's not like you find L first, but you have to do all this simultaneously. So our job is to find T1, T2, TL minus TL and L, and then maintain the machine between each of these intervals, all optimally. So what I try to do is I was trying to solve, I want to give a story before I leave. I decided I'm going to solve the machine for 2 times between 0 and T. One is S, one is T. So remember, each of these machine will be maintained. So I can say, okay, suppose I buy the machine at S and sell it at T. Then I have a machine that goes from S to T, and I want to find out what is the optimal maintenance. I can do that for every S and T. And I was sitting in my office, and Tom Morton walks in, and I told Tom that I have solved all of these problems for every S and T, but I don't know how to do the rest. And it took him 1 minute or less to say Wagner-Whitin. That means Wagner-Whitin algorithm will allow you to go from this step to find capital T. Now, my problem was I hadn't yet learned Wagner-Whitin. It was my maybe first year or second year of my program there. I stayed only 2.5 years there anyway. So during my first year or whatever, I did not know Wagner-Whitin. We haven't learned the dynamic programming course yet. So I had to read Wagner-Whitin. And when I read it, I realized, yes, it does. Everything is done. So I write the paper. I go to Tom. I said, paper is finished. He said, well, I gave you the main idea. That's not always true, because I did the first part, he did the second part. But he said, I gave you the main idea, so I should be the first author, but you did the other one, so you should be the first author, so we don't know who's going to be the first author, so we flip a coin. This is the only coin toss I ever won in my life. I got the coin toss. The paper is now Sethi and Morton instead of Morton and Sethi, because of a coin toss. I also want to say one thing, that about 2 to 3 weeks ago, Tom Morton passed away. So I got this news from also my student, but theoretically Tom's PhD student, Suresh Chand, who is a professor at Purdue, and he sent me this news about a month or so ago that Tom had passed away. Okay, that's, sorry to say that, but that's my end of my story about this paper. And then when we come back, we're going to start here, and we will solve the problem all the way using the Wagner-Whitin all the way to the end. I think this is, personally, I think this is more or less, in some sense, completes the machine replacement maintenance problem for deterministic machines. And there are at least 2 or 3 papers that does this thing for stochastic machines, the machines that fail. After this paper was done, people have now some people have done that, and also I have done that with my student Annabelle, who was my PhD student here. So there were 2 or 3 papers that generalizes this problem with the Kamien Schwartz machine and not Thompson machine. I use Thompson machine, but Kamien Schwartz machine is more complicated because it fails. If it's TS, ST, it fails in between. What are you going to do? So it's a little bit substantially more complicated. So there's a paper in OR and there's a paper in some book somewhere, and that extends this paper problem to machines that can fail. But we're not going to cover those. So we're going to only cover this and then move on to the next chapter, which is chapter 10. So let me take a break, and we'll come back in 10 minutes. We'll come back. Okay? Okay, we'll see you. Okay, do you have this slide? Can you see it? Hello?
Yes.
Okay. So we are back at the chain of machine model where each machine doesn't have to be kept for an identical amount of time. And so that's a model that I was describing earlier. So consider buying a machine at the beginning of period S and salvaging at the beginning of period T, which is strictly bigger than S. Let the JST denote the present value of all net earnings associated with the machine. And to calculate JST, we need the following notation. So I'm keeping the Thompson model here. XSK is the resale value of the machine at the beginning of period K, and K equal to S plus 1 up to T. Okay, because it starts from S and goes to T, so we can find the value of the machine, resale value of the machine, we can find, but we can denote. PSK is the production quantity in dollar value during period K. And because remember, I am selling the machine at the beginning of period T, so the production can only happen up to T minus 1. Once again, I don't do it here now, but each time you, excuse me, each time you have a discrete time problem, you should try to figure out what is happening, where things are happening and when. So it's always to have a picture in mind of the periods. E sub Sk is the necessary expense of the ordinary maintenance, which we have. And Rsk is the production quantity minus necessary expense. UK is the rate of preventive maintenance, that is in addition to the necessary maintenance. So I am putting a few more things on Thompson model, which makes it just more interesting, but it is not. It's not really making the model significantly different in terms of its contribution. UK is the rate of preventive maintenance from S to T minus 1 because at the beginning of T, the machine is sold. So that's the last period of maintenance. CS is the cost of purchasing the machine at time S. This is now a new thing because we're going to sell a machine then buy a new machine. So we need to, and we have to find how many machines we're going to buy during this period. So we need to find the cost of the machine anytime we buy. So we need to have a formula or notation for CS to the cost of purchasing a machine at any time at the beginning of period S. And notice when we sell the machine at the beginning of period T, we will buy another machine, and that machine will cost us C of T. So this gives the cost of machine at every time during this. Rho is the discount rate. We have an upper and lower bound on the control, but remember I have an upper bound that depends on S. And the reason I want that is because S is the vintage of the machine. And each machine may have a different characteristics, so upper bound may depend on that characteristic. So it depends on S, the vintage of the machine, and the K, the period in which the machine is operating. Well, then JST is nothing but RK, which is our revenue from production minus the necessary expense, and minus the preventive maintenance, and I'm just assuming simply that is the cost of preventive maintenance in dollars, so I can just substitute directly. And for this machine, I want to include that I purchased the machine, so I want to subtract that cost. And I'm going to sell the machine at T, beginning of T, so that is the sale value of the machine that was bought at S and its discount rate. So that is going to be our objective function. Then we need to find out the dynamics of these guys, how the dynamics of these states change. So we need to look at that. So what I'm going to do, since we did not, this is in discrete time, this is Boltzmann form. We have integrand and we have a terminal value function, and this is just constant for this problem, but I want to include it in JST because I'm going to eventually need that. But for the control problem, this is just constant. You can remove it. It's going to give you the same control. So without that, the problem is Boltzmann form, and with that is just a constant term that is you could actually put on this side JST plus CS, whatever. It doesn't really matter. So how does R change? Well, R change by a function that we have to define. So the function should depend on the vintage of the machine. So there's S. And remember now, K is the period. So just like in chapter 8, we wanted K to give the period because otherwise it sometimes becomes a vector, the component of the vector. So I want the superscript to denote the time in discrete time. That's not always the case. Different people may do different notation here, but this is our notation. So the psi S is the machine, and the way it changes depends on control, of course, that's all, and depends on the period in which we are in. So that's about the most general possible function that you can invent or you can define for this equation, which is now the difference equation. We need a difference equation versus a differential equation. And initial condition is RSS, which is given. How does the machine salvage value increase or decrease? It's given by phi s, UKK again, and XSS. Now notice here I did something. XSS is the salvage value of the machine at the beginning of period S. Remember, we bought the machine at the beginning of period S paying that much. But once we buy the machine and it's in our hand, there's always a depreciation. You can never buy a car at $20,000 and immediately sell it for $20,000. You will probably sell it for 18, and whatever that difference 20% is, and that's your delta. So it's fixed. We just assume it to be fixed, and that is your out of the shop. Not that I will buy a machine and sell it right away, but my my notation for the salvage value require an initial salvage value, and initial salvage value is not CS, but it's 1 minus delta times CS. You can put CS if you want, but then there is no depreciation. Now, we have defined the problem. If you take that objective function and those two equations, the control problem is defined along with the bound on controls and stuff that we already had before. The control problem is defined. But just for teaching purposes, we never converted a Boltzmann form to a Meyer form in discrete time. We did that in continuous time. We did all of that, but in discrete time, we only had one chapter, and we in that chapter we did the maximum principle for Boltzmann form. But just to be somewhat different, I'm going to convert this problem to Meyer form. You can solve it without that, but I'm going to do it Meyer form just so that we have one extra teaching item in there. So just like we did the Meyer form, other places we now have ASK, another variable, which is the integral of this guy from S to K minus 1. And BSK is the integral of this one from S to K minus 1. If we do that, then these two guys become Meyer form, right? So they become AST and BST. And that one survives, SCS, and that one stays at this. So this is now a Meyer form. Everything other than this constant that we subtract, everything is at time t, which is the terminal time of this machine. Now we, as in Meyer form, we have four equations. Equation 1, equation 2, equation 3, equation 4. Because when you have ASK, we can write the delta ASK equation, which is just the integrand, or summand in this case. If you do the sum, this is called summand. If you do integrand, it's called integrand. So we have a summand here, another summand, and so we have four equations. And that is 0 because if this quantity is the same or less than S, then this is automatically 0. So ASS is 0, BSS is 0 because there's no sigma there. And so we got four equations, 1, 2, 3, 4. And we have, so we can either have this objective function and these two equations, or have that objective function and four equations. This is what you're going to do. Because we have four equations, we have four lambda adjoint variables. We have a Hamiltonian, which is each true, and each one is with one of the variables. And then we have difference equations for lambdas. Lambda 1 is minus delta A, delta B, and so on. And we have a terminal condition as in Meyer form. So we take the derivative of these guys, and we finally have these conditions. That means it's constant because 0, and so this is equal to 1 all the way. This is equal to -1 all the way. This you can integrate easily, and this you can also. This lambda 4t is this, but it's 0, so it is this. It is also the same. So we have lambda 1k identically equal to 1. There's -1, this one, and this one is just the integral of this guy, and so we have a sigma 1 minus rho, 1 plus rho to the minus I. So all of these are done. Okay, so there's no secret here. It's just maximum principle application to a discrete time problem with four variables. Most of the action comes in modeling this problem, and then the action comes when we solve this problem using Wagner-Whitin. That's a new thing. Now Wagner-Whitin is not new. What is new is the use of this here. So we define H by two components. One is in which there's a control variable, one is there's no control variable. And in control variable part is this part. We can take the derivative because these are function of pi and s. We can take the derivatives, maximize this, and all of that is possible. If you have more complicated problem, you have to show that there's a unique solution. If not, you have to do further things. But all of that is calculus. And so I have this Hamiltonian, and we will probably want to assume concavity of psi s and phi s, and then this would be 0, so it'll be easy to show uniqueness of the solution. And what I'm going to do is further simplify it, because my job here is not really to make a problem complicated. My job here is to show that I have a methodology that solves the chain of machine problem, and for that demonstration, I can be as simple as I want. So I'm going to assume if they're quadratic, then you can see that you can solve this problem by taking the derivative. When you set it equal to 0, the solution will be something like this. It will depend on s, it will depend on t, and it will depend on k. So this would be the solution of that. And then if that solution is between 0 and usk, which is the upper bound, then you have to set it to the upper bound. If it is in between, it's a singular control, then you set it exactly that. So this is very similar to the model that we have previously. We have 0 and a u and an in-between solution. So this is kind of done. What I'm going to do is to make it linear. So I'm going to actually do bang bang, and then if there's a singular, fine. If not, that's also okay. So here's a function which is linear. So it's uk, which is the control I have in time k, and it's the coefficient may depend on s and a k. S because the machine was bought at s, k because it's a period k. Same for phi, I can do this. So I have the linear function, but I need to define these for each s and k. That means this can be defined like as a table or a function of s and k, whichever way you want to define it, it's okay. And I will define it different ways just to make it more interesting. If you do the linearity, then you can find that this function is linear, and I will define that to be our switching function, which is this. These are the coefficients, and this is the switching function in the sense that Hamiltonian has control as a term which is this times uk. So this is the coefficient of uk, this one. And our solution will be bang bang. So if the solution is positive, we have usk. If negative is 0, and this is true for s plus 1 and t minus 1. So we have the form of the control, and the problem is solved. The problem of each machine from any s to any t is solved. Once I have solved the problem, I can compute all the state variables on the optimal path. I can find JST star for any t bigger than s. That's where Morton comes in. So I'm here already, and the Morton says Wagner-Whitin, so this is Wagner-Whitin. It's a dynamic programming, straightforward. We have solved this problem when we did the traveling salesman, which is very similar. So this is traveling salesman's problem, kind of problem, very similar. So for Wagner-Whitin, I do the following. Let GS be the present value of an optimal solution from small s all the way to t minus 1. So I have a problem that begins at s and goes all the way to t minus 1. And of course, at the end of t, at the beginning of t, we solve the machine anyway. So that will be included in this. This is a preventive maintenance policy for all s up to this. We don't need this for t because g of t is already known to us to be 0. Yeah. Okay. So then, if you use this just like traveling salesman, we can do the dynamic programming. So suppose I do the dynamic programming, then GIS has to be defined by, I begin from S to T, some machine where T is arbitrary in some sense, or T is unknown. And then once I solve this problem, then at the end it's going to be GT. So the dynamic programming says the GS should be max of this over T. Because regardless of what the solution is, if I begin with S, there will be some T at which the machine would be sold. And that T could be anywhere from S plus 1, because I don't want to sell the machine S machine right away. I have to keep it at least for one period. That means I'll sell it at S plus 1, or I sell it S plus 2, or I sell at T. And then the boundary condition is GT equal to 0. The value of G0 will be required minimum. So I solve this dynamic programming, I have to go all the way to 0. It's a backward induction. I start from GT, then I go all the way to 0, G0. So that's Wagner-Whitin. It's simple, but that's what it is. So now, in order for me to do a numerical example, I'm going to define size and phi's and c's and u's and everything. So what I'm doing is doing in a more interesting, colorful way, different ways to defining everything. So I'm going to do that. So CS, which is the purchase price of the machine, instead of giving you a table, I give you this. So I'm going to have only 0, 1, and 2. That's only my problem will only consist of these periods. And so if I buy the machine at the 0 period, I will pay 1,000. If I 1, then I will pay 1,500. If I buy at 2, then I'll pay uh, uh, this will be 4 times 5, 2,000 to 3,000. So machine price is increasing this way. But you can also write a table, three numbers, 0, 1, and 2. You can do that. But I want to do it this way. Rho is 0.06, delta is 0.25, use 100. So this is no problem. What do I do? For RSS is the net return of a machine purchased the beginning of S and operated during period S. Okay, that's just one period. So it's R00 is 600, R11 is 1,000, R22 is 1,100. So this is, we need this because we need initial condition. We need initial condition XSS. So we need to define that. And we need RSS. This is already defined because when we define CS, so we already defined this. It's 1 minus delta times CS. That one we need to define, so we are defining it this way. So we define all the initial values. Then we define size. So psi s, we want this control variable. So this control thing that we're going to define to be minus ds, where each period I lose this much value, and then I gain this much value by applying the control with some coefficient, which is the effectiveness of the maintenance, and altogether I have this. But in that, if I want to have this formula, I need to find out what the ds and as are. So ds, I'm going to do a table. So d0 is 200, d1 is 50, d2 is 100. I can also do a table on as, but as I'm going to do this way. So it's just a different way of doing it. So I did this. So we have D0, D1, D2, and we have A0, A1, A2 also by this. So XSS is given this way. We already know what is CS, so we know XS. Now the incremental salvage value function is given by one is we begin with CS and it loses some value in each period, and the other one is it increases in value because of the BS. So I need to define LS and BS. I already defined CS. LS I'm going to define this way. 0.1 for 0 and 1 and 0.2 for 2. And BS I'm going to define 0.5 minus 0.5. In an idea, you can define all as a table. It's a small problem, but you may have a functions from the literature. For example, I worked on a tractor replacement problem. No, I worked on forklift truck replacement problem at Weyerhaeuser Company when I was working for the summer as a master student. I had to work every summer and also worked as a PhD student this summer in different companies. And one of the company I worked was the company that was forestry company, Weyerhaeuser, and they had a forklift trucks and they had to find replacement. And I actually developed the replacement, their optimal replacement strategy for the trucks. And there you sometimes find the literature by the manufacturer of the forklift trucks that gives you some of these functions. And then you can use those functions. So once we have this formula, JST star is the optimal value, and machine purchase S and sold at T. And we will now solve our control problem first. So we need JST star for every S and every T. And for that, we have a bang control. So we have all the machinery so we can solve the problem. So one thing we need to know here is that W, the switching function is this given by this. And the switching function means that if rho minus AS, the sign of this depends on sign of this. That means that control will increase. Control will increase if rho minus is bigger than 0. It will be constant if it is equal to 0, and it will decrease if it's less than equal to 0. Most of the time, you want this to be true. So we want to assume this to be less than 0, which we already done. And so which means that control can switch from 100 to 0, stay at 100, or stay at 0. There are only 3 possibilities. Okay, we already talked about that before. So if S0 is 0 and S is 0 and equal to 1, which means I buy the machine at the beginning of period 0 and sell the machine at the beginning of period 1, I keep the machine for 1 period. My switching function is exactly this one, which is less than 0. Because it's less than 0, bang says my control will be 0. So the machine I buy at 0 and sell at 1, optimal maintenance is 0. This is maximum principle. So if I have maximum principle, I can, once I have U0, I can find all of the R's and S's for that control using the difference equations. Like R0 is 100, 600, R01 is 6 minus 2, and so on. And I get the optimal value of this system, 01, J01 star. It's $213.20. Then for S equal to 0 to equal to 2, I get this. I find the control is 0 again for both periods, and the value of the machine that begins at 0 and sold at 2 is this. Some that begin at 0 and sold at 3, I find the control is 100, 100, and 0, and the J03 star is 639. They're all just, we already solved the problem, we're just using the numbers now. If I begin with 1 and 2, then I can solve again the problem, which is J1 2 star, then J1 3 star, and J2 3 star. And so we have basically solved all the problems for each period beginning, each period ending. Now the dynamic programming, Wagner-Whitin, we know G3 is 0. And G2, we use this formula. In this formula. So we have G3 0, we have G2, and there's only one thing going on here because there's only one period left. And so I can easily find G0 and then G3 0, so G2 is this. G1 says there are 2 possibilities. Either I can buy the machine at 1 and sell it at 3, or I buy the machine at 2. No, buy the machine at 1, sell it 2. But once I sell it 2, I need to buy another machine, but that value is G2, so I put G2 here. And I need to figure out which is optimal, so I take the max of these 2 guys. And the max of these 2 guys is 1024.2, which means the max of these guys is J13 star. So if I buy the machine at 1, I would optimal is to sell at 3. Then go to 0. It says max is 03 star, which is only one machine, or sell at 1 and then go with G1, and sell at 2 and go with G2. And take the maximum of these 3. Well, we all have those values, so maximum of this is 639, which we already computed before, which is 03 star coming from here. Yeah, he's coming from here. And so that's this one. Then you have 001 star coming from there, and G1 is coming from here. So we can put those guys here. And the same for this one, and we have this. So we know G0 is 1237.4. That's the best value we can do. And then we go back to find out what happened, because the G0 came from 1237. It came from this guy. And so we know that it's G01. It came from G01 star G1, so we just go here. So we can summarize the optimal solution. The optimal number of machines is 2, and the optimal purchase times are as follows. First machine optimal policy, purchase at 0, sell at 1, and the optimal preventive maintenance is 0. The second machine is purchase at 1, sell at 3. The optimal preventive maintenance policy is 100 and 0, and the total value is 1237.4. So, Sethi-Morton model, in summary, define a discrete time control problem where machines can be replaced and new machine can be bought. We're assuming that the machine that we buy are only one option is available, that is the new machine. You can extend this model, and we have done it somewhere. There are papers written without maintenance where you can do this even better, where at each point when you sell the machine, you have many options to buy. You can buy the most current technology, or you can buy older machine if they're still available. So like cell phone. When I bought my cell phone, I decided I don't want to go all the way because I still wanted a home button. So I went for 7. So after my S+6, I went to 7, and I still have 7. And one day when I sell 7, I will have an option to buy 8, 9, 10, 11, 12, 13, and maybe 14. Who knows how I keep it? So I have many choices, and that has to be optimized. So then you have to decide not only when to buy the machine, but also when to sell the machine, but also which machine to buy. And we have papers in management science where we said there's improving technology and there are different technology machines available, and you can buy what you want, and you can do optimal solution. But there we don't do maintenance because you can do it, but it just makes it more complicated. So that's gives you a methodology of any equipment regarding maintenance and replacement in a setting where nothing is breaking. If things break, you have no choice. If your cell phone breaks, you have to buy another one or live with that one. And that means that you need to figure out much more complicated problem. And it is not a simple extension of this in the sense that you need to worry about each time you have ST, you also have a possibility that the machine breaks down, and then you have to replace the machine at that time. So you have to have a lot of stuff. And Ali Dogramachi and some person from Cornell, from Columbia, they wrote a paper in operations research. Ali Dogramachi was a president of Bill Kent University. He was a good friend of mine. He is a good friend of mine. He's still around. He lives in New York now. And then Ali and I wrote a paper that extended that paper, and we were not successful in publishing that into a top journal because they thought that it's more technical stuff. And so we published that in some book. Or is available. Okay, so that's kind of the state of the art of this problem, and we will now move to chapter 10. Homework has already been given to you by Gautam. I just saw the email and I agreed with that homework. It is the homework that I had in mind. So we move to chapter 10. Is there any question on chapter 9? Okay, it's a lot of things going on in chapter 9, and it I believe is a very nice chapter. Even though machine maintenance and replacement is not a hot topic today, for example, but that's what it is. But it could be that you can formulate it as a stochastic control problem. One can actually take the Ben-Susan-Sethi problem, which is a rework of Kamien and Schwartz, and take that one step further to make that as a chain of machine problem. And that would be certainly very interesting contribution, but that's that. Okay. We are going to go to chapter 10. About 25 minutes. By the way, on April 14, I have a dental appointment at 4. So I think 3:45, when we finish the class, I still have 15 minutes and I only need about 10 minutes to go to their office. So I might leave exactly at 3:45 or leave maybe 2 minutes early. Okay, so just to let you know, that would be on the 15th or 14th. Chapter 10. Let's go and give you chapter 10. I'm going to stop that sharing and share chapter 10. Now that is an important topic. It continues to be important, and with the with the new world order, with Ukraine going on, there is a huge emphasis on global warming. There's a huge emphasis on what the Europe is going to do when they don't want to buy oil and gas from Russia. Right now, they are having big problems in the sense of not enough energy if they don't buy gas, so they are reluctant on that. But right now, they're going as far as not buying coal from Russia. But I have a feeling that it will be going further on that, because that Ukraine war is not going away anytime soon. So I have chapter on natural resources, and I have basically 3 models here. One is a fishery resource model, where it's a renewable source. It's like fish, food, and timber. Other one is a forestry model, which is also a renewable resource. So those 2 I will discuss. The third one I will not discuss is the exhaustible resource, petroleum and minerals, for example. There have been a number of exhaustible resource models in economics, and my model on exhaustible resource is not. I mean, it's nothing in terms of how you model the dynamics and everything is standard in some way. But what I do is, instead of maximizing a profit for the oil company, I solve 3 problems. I solve the problem of maximizing the profit for oil company. I solve the problem to maximize consumer surplus. And I solve the problem of maximizing alpha times consumer surplus plus 1 minus alpha times producer surplus. So that is an objective function which is different from what is in the literature at the time. And when alpha becomes 1, you got the company maximizing profit, and if alpha is 0, you have the social welfare maximization, and so or the consumer surplus maximization. And then I analyze the problem. What happens is alpha goes from 0 to 1. But the problem I don't cover in the class is only because it is it it doesn't give you anything new in terms of control theory, and it is a little bit messy because of the alpha going from 0 to 1 and analysis of that. But it's there as a model of exhaustible resource in the book, because you need renewable and exhaustible resources to complete the title saying application of natural resources. But I'm going to cover only the first two. The model is due to Colin Clark. And as I mentioned to you, maybe I did or maybe I didn't, but I think I did. After I did the Vidale-Wolf advertising model using Green's theorem, there was a substantial amount of literature that followed my application of Green's theorem to management science problems. And one such model, or one such follower model, is Colin Clark's model of the sole owner fishery. And it also used Green's theorem, so we're going to use the same thing. And so to that extent, we don't learn too much. But I like this model because Colin also did another extension of this model, which is the game. So he had a game model in which there are multiple fishermen fishing in the same lake or same catchment area, and then he solves the problem completely also, and also uses Green's theorem to some extent in there as well. So that's new. So in order for me to put the fishery thing in the game chapter, I decided I will use also his fish model in chapter 10, so that when we go to game theory chapters, we have a beginning base. And also, it's a nice model. He's a math biologist. He has a book on mathematical biology, and he also worked in practical cases of fisheries in British Columbia. So anyway, and he's a professor in math department, or was. Rho is the discount rate. XT is the biomass of fish population. That means some kind of concentration of fish in this lake. So let's just call it lake. Fish multiply, and that's called the natural growth function. So we're going to assume that given by these guys. UT is the rate of fishing effort at time t. So you put some effort to fish, and when you put that effort, you're going to catch some fish, which will be assumed to be proportional to the effort. Q is the catchability coefficient, which means how good a fisherman you are. P is the price of the fish that you catch. And C is the unit cost of effort. So C times U will be the cost of using effort U. We know that G0 is 0. If there is no fish, there won't be any fish. We also know by literature that if there is a huge amount of fish sitting in there, then there is no growth. There's a saturation capacity beyond which the fish don't have enough food to grow, and also they may have to eat each other and whatever. There's some X at which the growth is 0. So the growth function goes from 0, goes up, and then go down like that. So Gx is bigger than 0, between 0 and X. And the X is called carrying capacity in the literature. And it is the maximum sustainable fish biomass. The state equation is older than Colin's model. This comes from Gordon Schaefer in 1954, 1957. They decided that X dot is growth rate, Gx, minus the fish you catch. So it's proportional to U, which is the effort. It's proportional to biomass, which is X, because more fish there are, more you will catch. And it's proportionality coefficient is Q, which is the catchability coefficient. How good you are. So Colin Clark uses that. And using that, Gordon Schaefer don't do any optimal control. Pontryagin stuff was not even around then. And anyway, their purpose was not to optimize. Their purpose was more to find dynamics of fishing. And Colin Clark defined the objective function, which is rather simple, because if you catch that much fish and the price is P, that's your revenue. And if you use that much effort U, then your cost is CU. So your profit rate is that. And this is don't have to be imposed, because if I begin with any X, I'm going to stay. Because if X is 0, then, oh, that's not quite true. If X is 0, then this X is 0, so this is 0, so X dot is 0. So if X is 0, there's no fishing, nothing is going to happen, everything is 0 all the way, so the problem is, but if X is capital X, then this is 0 and that's negative, so X dot can only decrease. So we don't have to specify these constraints, they are coming free to us. So we don't have to do chapter 4, we only have to do chapter 3. And then you're doing Green's theorem anyway. So what Gordon Fisher said, that if there's an open access fishery, because every Tom, Dick, and Harry is going to go and fish there, then in the end, there is something called the bionomic equilibrium. And the bionomic equilibrium is equilibrium where the total revenue equals total cost. So basically, all the rent dissipate. Economic rent is dissipating, which means that this guy becomes 0. So that means XB, which is the bionomic equilibrium, is exactly C divided by PQ. And to maintain that XB, you put that X dot equal to 0, you find U, so UB is this number. So this is the control bionomic equilibrium. This is the state of the biomass in equilibrium. And the idea is very simple. If there's an economic rent, then another fisherman will come to make money until the rent dissipates. If there are too many people fishing, where the rent is negative, then some people will leave because they are not making any money. And in the end, it will result to bionomic equilibrium. So the equilibrium is the stable equilibrium. If it deviates, it will go back to it. In order to make life simple, I'm going to assume that this UB is less than U. And that way I can have interior solutions. And so those are our assumptions. When we do the control theory, we're going to assume this U is bigger than this quantity. So Gordon Schaefer basically does bionomic equilibrium. Now we're going to do actually optimal solution. And the optimal solution is going to be as follows. In the sense that bionomic equilibrium, there is overfishing. That means it's not good for the society to have open access fishery. And so if you were to have a controlled fishing, then you will see that the guy who's going to maximize his profit will not go to bionomic equilibrium. So if I was the owner of the sole owner model, I own the fishery, then I will not exhaust the fishery to the bionomic equilibrium. I will have a biomass which is bigger than bionomic equilibrium, and I will keep that biomass. And that would be the optimal biomass. Okay? So we will going to find the optimal biomass and the control that is required to maintain that optimal biomass, which will be optimal. So there will be optimal solution. So let's go with it. That's our objective function. That's our constraint. And we already have the state equation, which is 10.2. And doing Green's theorem, I can solve the equation 10.2 for u. I can have the u equal to this. Then I substitute for u here, which is right there. And I put x dot from my equation, x dot equation. And when I do that, I can simplify this expression like e to the minus rho t m of x n of x times x dot. That means term without x dot and term with x dot, where mx is given by this, and nx is given by this, and mx is given by this. That means you substitute for x dot, simplify, form this form, you will see that our equation, our integrand will become like this, where m and n are like this. That can be all done. Then I put x dot as dx dt. When I do dx dt, the dt will cancel out here. So this will be dx. And that dt is already here. So we will have a line integral. The line integral is that times dt plus that times dx. And any trajectory, on any trajectory, that line integral will give me the profit of that trajectory. Not optimal, but profit of that trajectory. So I'm going to use the Green's theorem in it and make it an area integral. Area integral is on any closed curve, which has an area gamma enclosed by that curve. I will have that line integral into an area integral, and the area integral is delta delta t of nx minus delta delta x of mx. That's the Green's theorem formula. You take the derivative with respect to t of this quantity, and you take the derivative of x of this quantity, and then you do dt dx, so the area integral over R, which is surrounded by this curve gamma. And you can write that as nx plus m prime x dt dx, because there's m prime x coming from delta dx. So you can write it this way. Then you can define, like we did in Wheeler-Wolf model, we integrand to be this way. That one then becomes this formula here. So I have n and m. I mean, I don't even introduce m and n. If I don't want to, I can just keep going and skip all these steps and come straight to here. Then our j gamma on the closed curve is integral over r given by this. And just like in Vidal-Wolf model, we want to find out what is the zero of this function. So we set it equal to 0. And we set it equal to 0. We can easily see, this is again, you can show that ix is less than 0 for x less than x bar, bigger than 0 x bar. So there's a solution called x bar. We're going to assume x bar to be a unique solution, and you can put conditions, and that's not a problem. So we can find x bar, and then you can find u bar that sustain that x bar. And because we assume this guy here, we'll find that this u bar is going to be interior solution. So u bar will be less than u, right here, for example. And so before I do that, let me go to the picture. So after we have done this, we already got this far. So this is my x bar. If I have a big biomass, I will fish like mad at highest rate allowed, and I will come to exactly this x bar. Then I will go to singular control and maintain this biomass at u bar. So the biomass, optimal biomass is u star, which is equal to u bar. If I have a very little biomass, I'm not going to fish for a while. Let fish recover to x bar, then I will go here. Very simple, nice solution given by Green's theorem immediately. But the Green theorem doesn't tell you what, it doesn't tell you very quickly what this means. What is this counting means? It doesn't look anything that you can just grab at it and say that's what it means. There's a divided by qx squared, there is d prime, there are a lot of things going on. We don't exactly know very quickly what it means. So this one, also Colin Clark being mathematician, that doesn't do that. He doesn't do that in his paper, as far as I remember. So I'm doing it. So in order to do that requires a little bit of a work. It's not so straightforward. But the way I do it is as follows. First, I say let X be any biomass. If X is any biomass, then I can find U for that biomass using the X dot equation, and then substitute that U and find the profit at that biomass, the profit rate that's given by pi X. So this is just formula for any biomass X. So what I want to show is the following. This is another way of looking at it. We didn't do that in Vidal levels because it was a little bit easier there. What I'm saying is that if this is my biomass, what happens if I change this a little bit? Would I come back to this optimal solution? Kind of. So what it's trying to say is if my biomass is x bar plus delta or x bar plus epsilon, then I will only come to x bar plus epsilon and then go here. And that should not be more optimal. That should not be optimal. That should be, if this is optimal, right? So that's what we're trying to do. So we want to find the profit associated with x. We take the derivative of that. The derivative is given by this. You can now see what I'm coming at. This is an indirect way, somehow call it a clever way if you want, to get to this thing. And if you see the formula here, there is some quantities that look like that. So that's sort of what we're getting at. The interpretation of pi x is that it is sustainable economic rent at a fish stock level of x. Because at that level, u is going to be qx by this, and then you multiply by p and whatever. So you get that. Suppose we have attained this equilibrium level x bar, and suppose we reduce the level x bar to x bar minus epsilon by removing epsilon amount of fish instantaneously from fishery. So what we're trying to do is have a x bar as a biomass, and then we just take a shovel and just remove the fish instantaneously, epsilon amount of fish. If you take that out, then the number of fish or the biomass is x bar minus epsilon. But if you take that much fish out, then that amount, by removing epsilon amount of fish instantly from fishery, which can be accomplished by an effort of this quantity, because we need some effort. So this is like an impulse control. You can make an effort with u and then integrate it over a while, but that will take some time. But if you do just impulse, that's the cost of that effort. And so we can do this kind of effort. So the immediate marginal revenue, MR, is this, because first of all, we get revenue. The revenue is PQ x bar epsilon divided by QX bar. Remember, QX bar cancel out. And so it's P times epsilon. We took an epsilon amount of fish. We can sell that fish at P price, so it's P times epsilon. And the effort that we need is U. So C times U is the cost. So this is the marginal revenue of getting instantaneously epsilon amount of fish. But if I'm going to remove epsilon amount of fish, my biomass will be x bar minus epsilon, and my biomass epsilon will suffer. Pi prime x times epsilon will be my cost of I will decrease the, sorry, why am I going here? I will decrease my sustainable rent by pi prime x bar times epsilon, which is easy to see. And that is the rate, sustainable economic rent. So I have to integrate that from 0 to infinity, discount it. And so my total loss of doing that action and keeping so taking epsilon amount of fish out and keeping the new biomass all the way to infinity will give me that value there. Okay? Now, add the cost of additional fishing effort. So then we get this is the decrease, and this is another decrease. So my marginal cost is given by that plus cost. So I have marginal revenue and I have marginal cost. And if you equate this and equate this, you equate this to this, you will see we exactly get 10.14. We get exactly, why 10.14? Why not do 10.14? Yeah, we get 10.14. The 10.14 is exactly, you can see 10.13 is nothing. In view of 10.13, I can write, remember I told you that this gives you a little bit like that. So if in view of 10.13, I can write 10.12, sorry, I can write 10.12, which is this. I use that formula. I can write the 10.12 in terms of pi. So writing 10 in terms of pi is this. This is also 10.12, given in a form that I can see a little bit more. I can see more here than I can see here. I see nothing here. I see almost nothing. But here I see a lot. I see what this is. I see what this is. Everyone has a meaning. The terms have a meaning. When 10.12, there is no meaning. So now I only have to show that my marginal revenue equal to marginal cost gives me this equation or this equation. They are the same. So if you equate those two, see, this is something you have to do at home. When you read this book, you have to see this, you have to see this, and when I say equate this, you get 10.14, which is same as 10.12. You have to do this. This is not something, in the old days when we used to board, we were able to do that. We will equate that and do this on the board. But if you don't do in board, it requires like 5-6 expressions and write them down. It's not done anymore. So this is what you do. You can take my words for it or do it. But if you do it, you will retain more. Okay, so I think we're going to stop here. I wanted to, well, let me, if you don't mind, let me take a couple more minutes. Is that okay, guys? Hello?
Yes.
Okay, so let me be this important. Economics people call something called golden rule. So the golden rule is as follows. Golden rule means take the biomass and optimize over the biomass. That means not optimizing the optimal control problem, which is the profit from 0 to infinity, starting from some initial condition. But it says, if I can choose the biomass, so this biomass, this biomass, this biomass, this biomass, which is the best biomass? So when the discount rate is 0, the equation 10.14, which we derived, actually reduces, it's 10.14 is right sitting here. If the discount rate is 0, then d pi x, pi prime x is 0. So pi prime x equal to 0 is the equilibrium level of fish stock when rho equal to 0. And it maximizes the instantaneous profit rate. It is also called the golden rule. So the golden rule can be obtained by setting rho equal to 0 in an optimal control solution. That's one way to do it. Another way to do it is to just optimize the integrand with respect to x, which is maximizing this quantity, which is the same. you maximize this quantity. The only way to maximize this quantity is to set pi prime max equal to 0. Because that is the quantity which gives you a solution of choosing the best biomass. If you don't have anything and somebody says you choose the best biomass and you must stay there, then you choose this biomass. And that's pi prime max equal to 0. So the question now is very interesting. And this question has a lot of people don't understand this. So I will only tell you a little bit, and then maybe we'll continue this later. So right now I'm saying if x bar at rho equal to infinity is bionomic equilibrium. If rho equal to infinity, future doesn't matter. Everything is now. So if everything is now, then the optimal solution of a sole owner is the same as the optimal solution of open access fishery. It's almost like free for all. Everybody is going to fish and reduce the level to XB. But if I'm alone and fishing and my row is infinity, I also don't care about the future. Then I will do the same thing as if all the other people are doing. So rho equal to infinity, we have bionomic equilibrium. Rho equal to 0, we have golden rule. And you can sort of see here the x bar for rho bigger than equal to 0. I think I should put rho here. Why is rho not here? Rho equal to 0, rho bigger than 0, rho equal to infinity. There should be a rho here to make it more clear. So rho equal to 0, x bar is bigger than rho bigger than 0 and is bigger than rho infinity. So the optimal solution for any rho lies between the bionomic equilibrium and the golden rule. And I want you to go home and think the following. So I'm at x bar. That's not the optimal that's not the golden rule. Golden rule is another x bar. So suppose, because golden rule is among these lines, the best line. So suppose the golden rule, which is bigger than x bar, we already just found out. So golden rule is bigger than x bar. So let's say golden rule is here. And I give you the golden rule. If I give you the golden rule, and if I want to maintain the maximum biomass, optimal biomass all the way, then I will just go like this. I will do the golden rule control and I will stay there. But it's not optimal, right? The optimal will say, take the golden rule level and then decrease to x bar and then stay here. I want you to think why, if you are given the best steady state level among all the steady state levels, you're given the best steady level that you can think of, and yet you don't want to keep it. If you are sole owner, you don't want to keep the best level. You want to reduce it to another level and then stay at that level, which is not as good as that. Because that level and that level, this one is worse than that one. But remember, we are not comparing that and that. We are comparing that and that. We're going down and then this. So there are two different paths, right? So think about why that's happening, and we will come back and talk about this more. And then we will move to forestry model. And then we also hopefully even go to chapter 11. So we are a little bit ahead of the game right now. You're solving the problem only, or what are the solutions? You're solving 9 and 10, right? The homework is 9.8, 9.14, and 10.8.
That is correct.
Yeah, but please read chapter 11. Even though homework is not in chapter 11, you need to read chapter 11. Okay, thank you. Bye now.
Thank you, Professor.
Thank you, Professor.